The binomial probability distribution is a widely occurring discrete probability distribution. It is characterized by the following. There are only two possible outcomes in a particular trial of an experiment. The outcomes of the trial are mutually exclusive. Each trial is independent of any other trial, which means that the probability of success does not change from trial to trial, and the random variable is the result of counts. So an experiment is said to be binomial if it meets the following characteristics. The outcome on each trial of an experiment is classified into one of two mutually exclusive categories, a success or a failure. The random variable, which we denote as x, counts the number of successes in a fixed number of trials. The fixed number of trials is the sample size n. For each of these trials, the probability of success and failure stays the same, and finally, the trials are independent, meaning that the outcome of one trial doesn't affect the outcome of any other trial. For a binomial experiment, the probability of observing a certain random number x, given the probability of success p and the sample size n, can be computed using the formula shown here. The formula contains three components. The first component represents the number of combinations x items can be taken from n trials. The second component is the probability of success represented by pi raised to the power x. The third and final component is the probability of failure, which is 1 minus pi raised to the power n minus x. We illustrate the binomial situation and compute probabilities for the sample problem presented on this slide. There are 5 flights daily from Pittsburgh via U.S. Airways into Bradford Regional Airport. Suppose the probability that any flight arrives late is 0.2. What's the probability that none of the flights are late today? So in this problem, the sample size is 5. The probability of success, that is, a flight arriving late, is 0.2. Each flight has only two possible outcomes. Either it is late or it is on time. Since we wish to know the probability that none of the flights are late today, the variable of interest, x, takes the value 0. Using the binomial formula, we substitute 0 into x, the sample size of 5 into n, and the probability of success, 0.2. Solving the binomial formula, we obtain a probability of 0.3277. We say that the chance that none of the 5 flights from Pittsburgh via U.S. Airways into the Bradford Regional Airport will arrive late is 32.77%. This slide shows the computational formulas for determining the mean and the variance of a binomial distribution. To solve these, we need to know the sample size n and the probability of success, pi. We apply these formulas to the Bradford Regional Airport example. Returning to the Bradford Regional Airport example, we apply the formulas for computing the average number of flights that are late flying into the airport in Pennsylvania in each day, if each day there are 5 flights and that the probability of any given flight being delayed is 0.20. So given this information, we compute the average number of late flights by multiplying the probability of a late flight, which is 0.2, by the sample size 5. The average number of late flights is 1. Given the same information, we compute the variance of the number of late flights by multiplying the sample size and the probability of success and the probability of failure. Symbolically, this will be n times pi times 1 minus pi. We note that the probability of failure is the complement of the probability of success. So substituting the Bradford Regional Airport information into the formula, we obtain the variance as 5 times 0.2 times 0.8. The variance of the number of late flights is 0.8. On this slide, we show another way of computing the mean and variance of a binomial distribution in a tabular form. the first step is to multiply x by the probability of x, denoted by p of x. You can see it right here. The resulting products are in the third column, right here. We sum up this column to obtain the average of 1.0 late flights, right here. This average is then subtracted from each of the x values in the first column, right here. These differences are squared and then multiplied by their respective probabilities as shown in the last column. So they're squared here and then multiplied again here. Adding up the values in the last column yields the variance of the distribution, which is found to be 0.7997.